Okay, today I'm going to be talking about Predbat internals and specifically in this video about the actual prediction algorithm itself. So the prediction algorithm is all based in the prediction.py file, and this is the main prediction function called run prediction. And essentially, what it needs to do is take in some parameters about your system and then produce a prediction as to what's going to happen in a 5 minute period from now until the end of the plan. So what you'll notice here is that some of the inputs here are on the function itself. These are the things that we change as it tries different options when it's building the best plan. So the charge limit and charge window, this is like the time periods you're charging from and what percentage, and the discharge time periods in the discharge window and the discharge limits. Whether you're running the PV 10% scenario or the normal scenario, and end record is essentially how long is the plan in number of minutes. Save says whether this is just an intermediate calculation or whether further data needs to be saved out. So these would be the things that would appear on the charts and all that sort of thing. And the step, it would normally be a 5 minute, but actually for the earlier phase where it's doing the leveling, it runs in 30-minute steps. So it runs quicker because they're rough planning. All the other values that come into here essentially come from the class itself because they're globals and they don't change per run. And part of the reason I've done that is because this runs in separate process pools. And so each process pool is like a separate process that runs, and it essentially takes the parameters across a network slot internally, and then runs a prediction and passes the data back. So all the things that are global are stored globally on each one of the processes to avoid all that communication overhead. So that'll be things like your energy rates, for example, and your solar predictions, etc. So all of those will actually be stored initially when you construct the prediction class and stored into this pred global structure. So essentially it stores all the member variables into there. And so when you run on the thread, it uses those globals which have been distributed to the different workers, so that it kind of sends it once. So it's an optimization. Wouldn't worry too much about that right now. So what happens when the prediction runs? So essentially it's selecting whether it wants the PV 10% scenario or the regular one. So these minute step values are essentially the values in 5 minute intervals that have been pre-calculated ready for the prediction. And things like the load minutes, for example, they've been pre-adjusted for any weightings and that sort of thing. The import and export of the energy rates. These are just outputs. These are things I'm going to store here, output data structures. And then it kind of starts at time 0 in the prediction. It sets a lot of the variables to the starting value. How much you've exported is how much it's already happened today and that sort of thing. And the final values are the values at the end of the plan as per the end record. And it'll actually run the plan on beyond that point, so the charts run further past the record period. Okay, so there's a few optimizations here. So as that each of the charge windows could intersect a discharge window, so discharge takes priority. That's like force export. So here, essentially, it removes the intersecting ones and it creates some to store what the new charge limits are and charge windows after the intersections. And it also creates an optimized array for like every 5 minutes for the charging and discharging, which window it is. Then record is true, so that runs until the end of the record period. Then we set some losses. So the inverter loss AC, if it's a hybrid inverter, is a loss. If not, then it's 1.0 because the losses are factored in another way. So they're essentially factored in with the normal inverter loss settings. So essentially we have something that runs each minute, each period within the forecast period. So while the minute's less than the end period. So it goes around this loop and it is going to increment the minutes each time. So it's a fairly simple prediction loop from that point of view. The 4-hour rule is something to do with the metric keep. So essentially, there's a rule that says that if you say keep 2 kilowatt hours in the battery, starting from now, rather than it saying immediately I have to have 2 kilowatt hours in the battery, it kind of scales the penalty for not having that for the next 4 hours. Because otherwise what would happen is, regardless of the rate, it would just start charging immediately. We don't want that, so it's kind of like fades in that rule over the next 4 hours of the plan. So then it's finding out whether we're charging or discharging, if there is, which window number it is. And it also finds out the charge limit. And there's something special here about if the charge limit is set to the reserve, that's actually a code that means charge freeze, and so it actually sets it to the current SOC is what you're trying to hold. And it also works out what the reserve would have been set to, because if you're holding, then the reserve gets set up to the hold level. And then once you get outside the end record, then record turns off. Then these things are just saving a time series. These are essentially for charts or for debug. So when you've got the save set to best, for example, it saves an array of what's happened in each 5-minute period, which can later be used to create the home assistant entities to plot charts, etc. So that's what these are being used for. Then standing charge is only added in the final sort of best plan. It's not used in the actual optimization calculations. Nothing we can do about standing charge. So that's just shown as the final values for costs. So metric is the cost that we're calculating for this plan. Here it's working out the amount of PV and the expected load for the next period. So this step here is probably 5 minutes, but it can be 30 minutes in the rough calculation. So it kind of adds them up for this period. Then if you've got a car, it works out the car load in the same period. This is if the car is not allowed to charge from the battery, then essentially the discharge rate is set to 0 if the car's charging, and that's kind of like a car freeze mode. If we've got iBoost enabled, then essentially there's some calculations here. So if you're using iBoost gas, then essentially you're only iBoosting when the rates are lower than gas rates. So it needs to work out the gas rate and the current energy rates to work out whether you're iBoosting. Then if you're boosting when the rates are low, gas rates are lower than export rates, it does the same thing. Then there is also the iBoost plan, which is essentially where you've done the smart mode and it's planned when to iBoost, and so it calculates the load for that one. Or if you're iBoosting when the charging, then if we're inside the charge window, the iBoost should run. And this is iBoost prevent discharge. This is turning off the battery discharge rate if you're iBoosting, if that's set. iBoost running is something that comes out to a sensor. So it says if you've got any iBoost, then it's going to be running. And then the iBoost load gets added into load today, which is the predicted load. So if the car's not charging, if the car is not charging from the battery, etc., then we reset the discharge rate to the full rate. And also we've got discharge freeze mode where charge is disabled, so we set the charge rate to the minimum. And then if we're inside a charge window, then we can also set the discharge rate to 0. And it depends whether we're actually discharging or not. there's some logic around that. And then we calculate a whole load of limits, including the minimum amount we are allowed to discharge based on the time period. And then essentially some code here that models the different modes of the battery. So if you look here, so discharge window greater than or equal to 0 means we're in a discharge window. So this is essentially when discharge is enabled on the battery. And here we're modeling that Predbat would cancel a forced export if we got to a period where there wasn't enough battery left for the limit. So it's just saying if it hasn't been cancelled already. And so it essentially works out what's going to happen when we're on forced export mode. And you've got to remember we've also got solar power and we don't want to lose solar power, so we have to balance that against the export limit. So if you've got an export limit of say 5 kilowatts and your battery and your solar power was 2 kilowatts, then you could only export the battery at 3 kilowatts, otherwise you go over the limit. So essentially it's scaling that back there. You also have a limit on the inverter itself. So depending on, so if it's a hybrid inverter and there's a DC input from the PV, then you have to invert that PV as well. And so your inverter can only invert a certain amount. So it has to scale back the battery export amount. And there's also some weird cases where if the PV was actually higher than the inverter limit, then you could actually charge the battery a little bit from DC instead, or then only inverting a certain amount of it. So that's a little bit complicated, and also then the 4-hour rule gets turned off once the battery starts doing a forced export. So this is to stop it from doing a forced export when you're actually below the metric keep. Then we have a charging code, which is quite similar. Essentially, we're in a forced charge window. We have to look at how much PV we've got as well and how much it can contribute to that, depending on whether it's a hybrid or not. And then there's some other subtle cases. There's something weird about, well, if we're modeling, say, a 5-minute period, but the battery would hit the charge limit after 1 minute, and actually the charge isn't spread over a 5-minute period, it's only for the first 1 minute and then it stops. So there's some potential weirdness here that you may actually cause imports even if you're charging from solar. So if you, let's say you've got 2 kilowatts of solar coming in and your battery charge rate's 3 kilowatts, well, you're going to import 1 kilowatt. But if the battery was nearly full and you only needed 1 kilowatt hour, then it's still going to import because it'll charge at full rate and then stop. Then eco mode is the other mode. So this is whether you're either forced importing or exporting. And in this case, essentially, the battery tries to balance to make sure that you're neither importing nor exporting. So the battery does the reverse of the load balance that you have in your system. And so there's a few cases on this one that it has to calculate, and also whether it's hybrid or AC. With hybrid inverters, there's also you have to be careful about the inverter limit. This actually gets quite complicated, and there's quite a lot of cases, and I wrote some unit tests for this one as well. In some cases, you're going to have to clip the solar because you can't actually invert any more than that. And if it's an AC coupled, it becomes a bit simpler as well, because you don't have a lot of these weird cases for charging the battery from DC. You have to follow the export limit that's been set on your system. And then obviously the battery has to go down by the amount that you're discharging it by, or going up by the amount that you're charging it by, and there's losses to account for in the system as well. And then there's also iBoost on solar that we have to account for here. So if iBoost on solar, it's assuming that that's going to be seen after the battery system sees it. And therefore any spare solar then could be diverted by an iBoost model. And so all of that is calculated, and when the iBoost starts running as a result. We also work out the battery cycle figure, which is essentially gets incremented by the amount that the battery is either charging or discharging. And then we work out essentially what's left over, which is essentially what's going to sit on the grid. So is it exporting or importing to the grid? And there's some complex logic about that in this get-diff function as well. Metric keeper is essentially saying if the battery level falls below the required level, then we add a penalty, pretend it costs more than it really did. And the penalty depends on this keep scaling, the 4-hour rule, and also for how much it falls, how much you would have imported if the battery wasn't there. So essentially, metric keep is pretending the battery might have run out sooner and then working out how much it could have cost you as a result. Then, depending on whether you're importing or exporting, we actually work out the costs of that and also the carbon footprint of that. And I assume exports reduce carbon footprint and imports increase it. And then essentially there's some information that's stored. So when we update these final figures up into the point where the recording stops. So we store the final figures at the end of record, and then we go on a bit further and plot all the lines with the charts. And then there's some information here out of the charging started and discharging started. And we record some state information. And so this just goes around the loop in the step until it gets to the end of the simulation, and then the final values are saved and it's returned. So it all sounds quite simple, but these calculations are quite subtle and it's quite easy to get them wrong. There is also a unit test for this as well. So if I look for run prediction here, it uses the run prediction single wrapped in the unit test, and it calls it various scenarios, and then it checks the results. And what you'll see here is that this thing called simple scenarios essentially running the simulation. And then there's a whole load of different scenarios here about whether you're charging or discharging and whether it's using the battery or not and how much energy is in the battery, and lots of checks here. So this will work through to try and find most of the bugs in it. It's possible something won't be covered, but I did do Python coverage on it to see how long it could be covered as well. So that's the main core of the prediction code. So then beyond that, the only other things you'll find is this global storage, which is essentially, like I said, for the thread pool here. So when you run a wrapped prediction, it essentially brings the data out of that global storage and runs the prediction. And these different functions are just different wrappers around it with different arguments. And then there's some helper functions. So get-diff is essentially working out what's on the grid based on the balance of batteries and solar and load. So it works that out with the losses, depending on whether it's AC coupled or hybrid. Get total inverted is for the inverter limit. It works out how much work the inverter has to do, again, if it's hybrid or AC coupled. And then the initialization for the prediction class and some more wrappers. The thread run prediction charge is essentially just something where you specify which window you're changing and what to value, and it just changes the windows for you and runs prediction and then returns the result. So it's just a helper function for the actual optimization code itself. So yeah, it's explaining each line of it is quite complicated, but it gives you a rough overview. And in iBoost slot just tells you whether this particular minute is in a slot that's on the iBoost plan or not, and in car slot tells you whether this minute is in the car charging plan or not, and if so, how much, essentially what load it would add in both cases. So again, they're helper functions. And that's about it for that, really. Thanks for watching.